Hello friends, my name is IBM, your physics companion, and I'm here to introduce to you another unit of solved past paper questions in physics AS, that is 9702. And today I want to introduce one of the large units, one of the units with the biggest number of questions, that is kinematics. And I would like to introduce kinematics today as one of the largest units. I decided to choose the smallest unit so that we could have so many questions, so that we could have so many topics solved. Remember, kinematics would have so many questions, and therefore it would take a long period of time, which by now would be having fewer topics. However, I decided that it should be one of the last. So after kinematics, of course, we shall be remaining with only electricity. So this is kinematics part 1, and this video could be long, but I know I'm going to try my level best to make it short. So this is solved past paper questions, and in kinematics, we are planning to go to discuss questions such as, you'll see questions about velocity, speed or acceleration. You'll see questions about distance and displacement. You'll see questions about this. Okay, we shall be describing motion. Equations of motion, projectiles, and a lot more will be seen in kinematics. And without wasting time, I would like to take you to the past paper questions. Do not forget to download the document which is attached in the video description. If this is your first time onto this site, you can print by topic, you can print per topic, so that it is easy to follow through when you have it in hard copy. So without wasting time, I would like to take you to the document, which is Master Key to A-Level Physics, Physics 9702, Revision Questions, that is paper 2. These are solved past paper questions, and therefore we expect to solve all the past paper questions. So I think we have finished solving physical quantities, units, and measurements in the videos. You can check if you are new to the site. We have finished solving dynamics. We have finished work, energy, and power, force, density, and pressure, deformation of solids. We have finished waves. We have finished particle physics. So we are remaining with kinematics and electricity. So without wasting time, let's look for kinematics. Kinematics is on page 43. Yes, here we are. Kinematics is on page 43. So complete the table by stating whether each of the quantities is a vector or a scalar quantity. So in a vector quantity has both magnitude and direction. A scalar quantity has magnitude only. I want to let you know that at our AS level, we expect only 6 vectors, that is acceleration, velocity, and displacement. Those are 3 from kinematics: acceleration, velocity, and displacement. Number 2, we expect momentum and impulse, because impulse is change in momentum. So at our level, we expect moment or impulse. Then we expect force as a vector. Remember, weight is a force. And lastly, we expect moment, or sometimes called torque. So these are the vectors we expect at AS level. That means everything else must be a scalar quantity. So from our table, it is only acceleration which is a vector, and the rest are scalars. The rest are scalar quantities. Then the variation with time t of the velocity v of an object is shown in the figure. So this is the figure. It is a graph of velocity against time. It is a graph of velocity against time. And our scale is 0.25 divided by 5, which I think is 0.05. 0.25 divided by 5, that is 0.05. This one small square on the vertical is 0.05, which means that this point here is going to be 0.7. And this point here is going to be 1, 2, 3. That is 1 point. 0.3 times 0.05. So times 0.3, I mean 3 small squares. These are 3 small squares. So I'm going to add that to 1.25, which is 1.4. So this value here is 1.4. So determine the acceleration of the object from t equals to 0 to t equals to 4. We know that acceleration is equal to the gradient, which is change in velocity, or v minus u over t. So from the graph, let's check out our v. Our v we have seen is 1.4. Then minus u, our u is 0.7. Divided by the difference in time, which is from 0 to 4 seconds. So the time here is going to be 4.0. So we can now check from our calculator the acceleration. So 1.4 minus 0.7 divide by 4. So that is 0.175. 0.175 meters per second squared, which is approximately 0.18. Determine the distance moved by the object from t equals to 0 to time t equals to 4 seconds. Distance. Going back to the graph, remember it is a velocity time graph. Distance is equal to the area under the graph. For a velocity time graph, the distance or displacement is the area under the graph. So we can take it as a trapezium, or we can divide it into a rectangle and a triangle. So distance is equal to the area under the graph. Area under the graph, which is a trapezium, and that will be a half into a trapezium is a plus b times height. Area of a trapezium is a half into a plus b times the height h. So we can say our a is from 0 to 0.7, our b can be from 0 to 1.4, and our h can be from 0 to 4. So our a is going to be 0.7, our b is 1.4, and our height is 0. It is actually 4, not 0.4. So that is times 4. So we can check this. A half is 0.5 times 0.7 plus 1.4 times 4. So that gives us 4.2. So this is 4.2. Alternatively, you could have divided that into a triangle and a rectangle. So here we are seeing that our distance is 5.2, but let's use another method, or maybe I will do the second method here. We can divide this into a rectangle and a triangle. So it means the distance is going to be, for the rectangle, we have maybe the length can be 4 times the vertical, which is 0.7, that is for the rectangle. Then plus the triangle, which will be a half, times the base, which could be 4, times the height, which could be from 1.4 to 0.7. That is 1.4 minus 0.7. So this would give us 4 times 0.7, that is 2.8, plus we have a half, which is 0.5 times 4 times the difference between 1.4 minus 0.7, which gives us 1.4. So this is plus 1.4. And when you sum up, you get 4.2 meters. So that is the distance. Question number or part C, define force. Of course, we know that force is the rate of change. Rate of change of momentum. That is force. Force is the rate of change of momentum. The motion represented in a figure 1.1 is caused by a resultant force F acting on the object. On figure 1.2, sketch the variation of F with the time t from t equals to 0 to t equals to 12.0 seconds. Numerical values of F are not required. Now, this is where I have made a mistake. I didn't capture the grid, but we can still first come up with this graph. We want to sketch a graph of F against time from t equals to 0 to t equals to 12 seconds. So, to begin with, remember force is equal to mass times acceleration. Where acceleration is constant, the force is constant. Do you notice that from t equals to 0 to t equals to 4, it is a straight line, which means acceleration is constant, by the way, not 0. It is a straight line, which means the acceleration is constant and not 0. They say the numerical values of F are not required. So it means I know for t equals to 0 to 4.0 seconds, the force is going to be a constant value. Force is constant. Then from 4 seconds to around this value here, which is 8 to 8.0 seconds, you see that the acceleration between 4 and 8 is 0 because the line is horizontal. Remember, from a velocity time graph, the acceleration is the gradient. From t equals to 4 to t equals to 8, it is a horizontal line whose gradient is 0, meaning in that case, if the acceleration is 0, the force is 0 between t equals to 4 to t equals to 8. Then from t equals to 8 to t equals to 12 seconds, again, this is a deceleration, meaning the acceleration is going to be negative. It is a negative acceleration. That means the force will also be in the opposite direction, because force is also a vector quantity. It is always in the same direction with the acceleration. Because the acceleration is negative, the force here is going to be negative. But I want you to note that when you try to find the gradient, in the first stage between 0 to 4, we found the gradient as 0.18. In the second stage, we can try to find the gradient. In the second stage, the gradient will be, which will be the acceleration, will be equal to, let's say, from 0 at the final value of v0 minus the initial, which is 1.4 at the top, divided by the time is 12 minus 4 minus 8, which is actually 4. And when you divide this, you have that 1.4 negative divided by 4, you have 0.35. 0.35. So you notice that actually the second acceleration is approximately twice. It is actually twice the first acceleration, because the first acceleration was exactly 0.175. Let's check 0.175 twice. 0.175 times 2. Yes, so the second acceleration is twice. So that means if the first constant force was represented by a certain magnitude, the second force is going to be represented by, it is also constant, but with twice the magnitude as the first case. So if I was to sketch this, let me just let me just come up with a simple grid here. Let me find a space so that I can put a simple grid. I'll just draw axes here. So if this is the vertical axis for the force, and this is the horizontal axis for time, between t equals to 0 to t equals to 4, the force is constant. That will be a horizontal line. Then between t equals to 4 to t equals to 8, the acceleration was 0, so the force is 0. That will also be a horizontal line along the x-axis. Then between t equals to 8 to t equals to 12, the force was also constant but was negative, and it has a higher magnitude because the acceleration is twice. The force must be twice the first value of F. So we shall draw a horizontal line at the bottom which has twice the magnitude as the first line. So if I change the color for us to see this graph, so we have a horizontal line here between t equals to 0, t equals to 4. We have a horizontal line here between t equals to 4, t equals to 8. And we have a horizontal line here between t equals to 8 and t equals 12. So I will just join this into a simple step, something like that. So our graph would look like this. For the first case, the force is constant because the acceleration was constant. For the second stage, the force was 0 because the acceleration from the graph was 0 since the gradient was 0. For the last stage, the acceleration is constant but negative because the gradient was constant but negative. However, the gradient was twice the first gradient. I also have a grid which I can use, but it is not in the document that you downloaded. So let me use the grid that we have. So we have seen that from t equals to 0 to t equals to 4, the velocity time graph showed that the acceleration was constant, so the force is constant. Therefore, I will draw the force as a horizontal line. The force is constant. Then from t equals to 4 to t equals to 8, the acceleration was 0, so the force is going to be 0. So I will draw a horizontal line along the x-axis. And from t equals to 8 to t equals to 12, we have seen that the force was constant because the acceleration was constant, but the acceleration was negative. So the force must be in the opposite direction because the acceleration was negative, and the acceleration was actually 35. It was 35. Which was twice the first acceleration. That means the second force is going to be twice the first value of force that we have indicated. So how my graph would be twice the first value, so the graph would be here. So this is the graph that we are expected to be able to draw. That is going to be our graph. It will be in steps. I think that is a simple concept. Even if the grid is missing, you can understand that concept very easily. Okay, let's go back to the other document. Define acceleration. Of course, we know that acceleration is the rate of change of velocity. Rate of change of velocity, that is acceleration. Rate of change of velocity, that is acceleration, or change in velocity over time. Acceleration is not just velocity over time, it must be change in velocity over time, the rate of change of velocity. A stone falls vertically from the top of a cliff, as shown in the figure. The variation with the time t of the velocity v of the stone is shown. So we are seeing that the velocity increases and then it becomes constant at some time. Let's see what velocities are the velocity which is constant, or when the constant velocity. Of course, the constant velocity is around here. And I think this is the scale on the vertical is 10 divided by 10, which is 1. So this is 1, 2, 3, 4, 5, 6. So that is 36. Okay, let's see the questions now. Let us see the questions. Explain with reference to the forces acting on the stone, the shape of the curve of the figure. So let's look at the shape of the curve. We are going to explain with reference to the forces. So a stone falls vertically from the top of a cliff. Since they didn't mention that air resistance is negligible, even the graph is showing that air resistance is not negligible. So let's think of a stone as this one. Its weight is vertically downwards. Motion is downwards. It is falling. So this arrow is showing that motion is downwards. That means the force due to air resistance is in the opposite direction. So the force due to air resistance is in the opposite direction. Therefore, we can now think about the forces which are acting here. The weight does not increase, but air resistance increases with the speed. If the motion is downwards, the speed increases when the object is moving downwards. That means the air resistance increases. And the resultant force F on this object is going to be the weight minus the force due to air resistance. If the air resistance increases when the motion is downwards, air resistance is increasing with the speed, it means the resultant force decreases. But you and me should note that the resultant force is given by Newton's second law, ma. If air resistance increases, the difference between weight and air resistance becomes smaller, where the resultant force becomes smaller. If the resultant force becomes smaller, it implies that the acceleration is decreasing. So the acceleration decreases as the resultant force decreases until a point when the weight equals to the air resistance, or when the air resistance balances with the weight. When the weight is balanced with the air resistance, it means the resultant force is going to be equal to 0. And if the resultant force is 0, the acceleration is 0. Zero acceleration now means that initial velocity is the same as the final velocity. That means the velocity is constant. Therefore, we are saying that air resistance increases with the speed. As speed increases, air resistance increases, which means the resultant force on the ball decreases, the resultant force on the stone decreases as speed increases, which also means acceleration decreases as speed increases. However, we have seen that when the weight equals to the air resistance, the resultant force is going to be 0, and therefore the acceleration will be 0, and therefore the speed remains or becomes constant. Okay, so we are saying air resistance increases with the speed. Air resistance increases with the speed. When a body is falling downwards, speed increases. Air resistance increases with the speed, and that means the resultant force decreases. The resultant force decreases as speed increases. The resultant force increases as speed, the resultant force decreases as speed increases, so the acceleration decreases. So acceleration decreases as speed increases. And when the air resistance equals to the weight, because the weight is constant, when air resistance equals to the weight, when air resistance equals the weight, the resultant force is 0. The acceleration becomes 0. Acceleration becomes 0, so the speed remains constant. Also, the speed becomes constant. So scientifically, we say that the body has reached its terminal velocity. So even in the graph, you can see that initially the speed is increasing, but the increase reduces as air resistance increases until a point at around 15 seconds when now the body reaches a constant velocity. At this point, we say that the weight, when the graph becomes horizontal, we are saying that the weight is equal to the air resistance. So the acceleration will be zero and the speed will remain constant. Okay. Use the figure to determine the speed of the stone when the resultant force on it is zero. The resultant force, when the resultant force is zero, it means the speed is constant. So we have to look for the constant speed. And the constant speed is, I think, 36 from the graph, where the graph becomes horizontal. So they said when the resultant force is constant, the resultant force is zero. When F equals to zero or acceleration is equal to zero, it means that the speed is constant. And the constant speed from the graph is 36 meters per second. Use the figure again to calculate the approximate height through which the stone falls between t equals to 0 to t equals to 30 seconds. Approximate height, that is a distance. And we know that the distance is going to be the area under the graph. So I will say that the height is going to be equal to the area under the graph. This is going to be quite hard for a normal student, but is going to be very easy for a serious student. Area under this graph, it is not a straight line this time, so it becomes hard for a student. But now you notice that we can first find a rectangle from this graph. So if I take a whole rectangle, I'm taking a rectangle from this graph. I'm going to take a rectangle, then I remove this area here. I will subtract this area here, which area I will also remove. I can make a triangle, then I remain with with a few small squares. So I'm making a triangle, which is a tangent. I'm drawing a tangent here so that I remove a triangle from this grid. I want to draw a serious triangle. We want the area under the graph, but we can first find the area of a rectangle, and then on that area we are going to subtract the other part on top, which is not under the triangle. So I'm drawing a triangle. No, I mean we first get the area of a rectangle. So the total area of the rectangle, including the unwanted part on top or above the graph, will be this is going to be 30 seconds times 36. That is for the whole rectangle. Then on this one, I am going to substitute the triangle, which I have drawn here. So I'm going to say minus. For the triangle, it is a half times the base. I will say the base is maybe, the base is going to be this one. Let me check. The scale here on the vertical, on the x is 0, is 5 divided by 10, 0.5. So this is 6, 7, 8.5. So this is 8.5. Let me change this triangle so that it is easier to use. I'm going to put it at 8. This is 6, 7, 8. Okay, so that is my triangle. Let me see this. So this is 6, 7, 8. So that is 8. So that is 8. Then this one is 1 point. This is going to be 12. So the triangle is going to be the base, which is 8, because this is 8, times the height, which is 36 minus 12, which is going to be 36 minus 12. 36 minus 12, that is 24. Again, I'm going to subtract now the remaining part, which is the small squares. I need to first of all find what one small square represents in area. One square in area is going to be equal to, on the x-axis, I have 5 divided by 10, that is 0.5. On the vertical axis, I have 10 divided by 10, which is 1. So one small square represents 0.5 meters, because it is meters per second times seconds, which is meters. So I need to find how many full squares do I have in the remaining part. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. The remaining are half squares. I'm coming this side, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. So I have 32 full squares. So the area for the full squares is going to be 32 times 0.5. That is for the full squares. Then for the half squares, the half squares are those ones which are not crossed, which are actually crossed by the lines. So I would say this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, no, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. This side I have 25, 26, 27, 28, 29. Then up there I have 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, around 48. So the half squares, area for the half squares, remember they are half squares. So if they are half squares, then it means the area is going to be a half of 0.5 times 48. So there are 48 squares. So we have this area for the full squares. These are the full squares, and these are the half. So the area for the full squares is 32 times 0.5. The area for the half squares is a half times 0.5 times 48. So we may not get an exact value, but what is very important is first of all to know the area represented by one small square. Okay, so we are going to transfer our working into the space provided. The height is going to be the area under the graph. So to begin with, the height is going to be equal to the total area of the rectangle, which we have seen as 36 minus 30. That is for the rectangle, minus the area of a rectangle, the triangle which I drew, which was a half, times the base, which is 8 times 24, plus for the full small squares I got, which were in between there. Remember, I'm getting the total area minus the area above, which is the area here. That's why I've been getting the area of a triangle. Then I remove the area of the small squares which are remaining. So this will be plus. The other one was 32 times, there were 32 full squares times 0.5. Then plus the half squares. The half squares were 48 times the area of a half a square, which would be a half, times the area of a full square, which is 0.5. So that is the total area, which is above the graph. And I have to subtract it from the rectangle. So I'll check this with my calculator. In the brackets, I have 0.5 times 8 times 24, which gives me that, plus 32 times 0.5, which gives me that, plus 48 times a half, which is 0.5 times 0.5, which gives me that value there. So this value is going to be subtracted from 36 times 30. So 36 times 30 minus the answer, which gives us 956. So this area here is 956 according to me, which is approximately 960. So since it is an approximate height, you may get values slightly different. So me, I'm getting 960 meters to two significant figures. You could get areas in the range between 920 to 980, depending on how accurate you are. So that is going to be the approximate height. Remember, note that method of getting such distances. Area under graphs which are not straight lines. Me, I use the simplest method of finding, first of all, drawing a rectangle. Then from the rectangle, I remove the area above the shape, which is not very easy, but I tried. You could also have divided the graph into other shapes. Maybe a rectangle at the end where the line is horizontal, and another triangle. Somebody would have preferred to say, okay, I will draw here a rectangle. Let me use a different ink. Somebody would have preferred to say, okay, I will use a rectangle here. So you first draw a rectangle around here. Then you draw a triangle. So you first get the area of that shape, Now you remain with this shape here, where you have to calculate to count the squares here and multiply by the area of one small square. You count the full squares multiplied by the area of one small square. You count the half squares, then multiply by the area of one full square divided by 2. Then you sum up. You will be able to get a value which is very close to mine. That is approximately 960 meters. Okay. On the figure 2.2, sketch the variation with time t of the acceleration a of the stone between t equals to 0 to t equals to 30. We have seen that it reaches terminal velocity at around, let's see, when does it reach terminal velocity? The velocity is becoming constant. Let me see, 15. The velocity is constant at around 20. We can become confident that the velocity is constant at around 20. At around 20, the velocity is actually, we can believe that is exactly constant at around 20, or a value close to 20. So at 20, we shall say at 20 the velocity is constant. Here acceleration should be equal to 0. Therefore, from 20 and below, or some value close to 20 and above, the acceleration is going to be 0. So starting with that part of 20, at around 20, the acceleration is going to be 0. So here I will draw a horizontal line because the acceleration is 0 at around 20. But before 20, from the graph, we see that before 20, the gradient was decreasing. That means the acceleration was decreasing. So it means if the ball was released from rest, the initial acceleration must have been 9.8 or 9.81. So our graph is going to start at t equals to 0 when the object is just released. Its acceleration is 9.8. It is due to gravity. So since the scale on the vertical is 5 divided by 10, which is 0.5. So 9.8, that is 6, 7, 8, 9.5. 9.8 is going, 81 is going to be somewhere there. So our graph will start from there at 9.8 or 9.81, somewhere there. And we are seeing that the gradient of the velocity is decreasing. The velocity is decreasing. Therefore, the acceleration is decreasing because there is air resistance. So the gradient must be decreasing until we reach 0. I mean, the velocity is having a decreasing gradient with the time. The acceleration is decreasing. So our graph should be decreasing. But the decrease becomes smaller. I mean, the decrease becomes, or the change in velocity with the time becomes smaller as time goes on after a certain value around 10. So the graph will be curving downwards. So our graph will look like this. Our graph will be a graph which curves downwards and it touches 0 at around 20. So that will be the graph of acceleration against time. So somebody would say, why isn't the graph curving upwards? Curving upwards would mean the acceleration decreases more rapidly as time goes on. But we are seeing from the graph that the acceleration decreases less rapidly as time goes on. That's why the graph is curving downwards. Okay. Number next, define acceleration. Define acceleration. We have already seen that acceleration is the rate of change of velocity. Rate of change of velocity, or change in velocity over time taken. That is acceleration. A steel ball of diameter 0.08 meters is released from rest. The ball falls vertically in air as illustrated in the figure. So they have showed us the position for the ball when released, and they've showed us position P of the ball when it is about to cut a horizontal beam of light of negligible width. A horizontal beam of light of negligible width is a vertical distance of 0.2 meters below the bottom of the ball when it is released. The ball falls through and breaks the beam of light. Explain why the force due to air resistance acting on the ball may be neglected when calculating the time taken for the ball to reach the beam of light. So let's look at the diameter of the ball is very small. It is a steel ball, but of a small diameter. That means the air resistance is going to be very small. Therefore, most likely we can say the weight is much greater than the force due to air resistance. The weight of the ball is much greater than the force due to air resistance. Why do we say this? It is having a very small diameter, meaning the surface area on which the force due to air resistance is going to act is very small. Therefore, we can say that the force due to air resistance is negligible compared. It must be compared to the weight. The weight is much greater than the force due to air resistance. Hence, the force due to air resistance is negligible. Then calculate the time taken for the ball to fall from rest to point P. I think that is simple equations of motion. Simply using equations of motion, S is equal to ut. S is equal to ut plus a half at squared. Since the force due to air resistance is negligible, the acceleration is constant. To reach position P, it falls through a distance of 0.28. Initial velocity in the vertical is 0 because it started from rest. That means initial velocity was 0. So this will be equal to a half times acceleration, which is 9.81, then times t squared. So that means t is going to be the square root of 2 times 0.28 divided by 9.81. So square root of 2 times 0. Square root of 2 times 0.28 divided by 9.81. So that gives us 0.239. So this is 0.239, which is approximately 0.24. Determine the time interval during which the beam of light is broken by the ball. The time interval during which the beam is broken by the ball. Remember, it is the diameter of the ball which is breaking the beam. So we need that only that time when the beam is being broken by the ball. There are two ways of doing this. Number one, we can begin by finding the total distance falling through if we include the diameter of the ball. And we subtract. We find the time for that total distance and we subtract the time if we did not include the diameter of the ball. So total distance falling includes also the diameter of the ball. If the ball crosses the beam, the whole ball crosses the beam. By the time the ball is here, it has finished to cross the beam. It means the total distance falling through is going to be equal to 0.28 plus the diameter of the ball, which is 0.08. So the total distance falling is going to be 0.28 plus 0.8, which gives us, I think this is 0.36 meters. Therefore, using again S is equal to ut plus a half at squared. We now want the time for this distance. So 0.36 is equal to a half because remember it starts from rest. Initial velocity is 0. So it will be a half times 9.81 times t squared. Again, we find t squared as the square root. We find the square root of 2 times 0.36 divided by 9.81. So square root of 2 times 0.36 divided by 9.81. That gives us 0.271. So this is 0.271 to three significant figures. Remember, this is the time for this distance. We have seen the time for only 0.28. So we can now just subtract the time interval. The time interval is going to be 0.271 minus 0.239. 271 minus 0.239, which is 0.032. So this is 0.032. So the time interval here is 0.032 seconds. Or if you use two significant figures, 0.27 and 0.24, you would get 0.03. That is fine. That is, I think that is the simplest method. I think that is the simplest method. However, if you are good at mathematics, you can also solve a quadratic equation. Let's use the space here for the other method. Method 2, I could first find the speed with which it arrives at the beam using v equals to u plus at. I can find the speed with which it arrives at the beam, so that I can now use that speed with the diameter of the ball to find its time after the time it takes to cross the beam. So v is equal to u, which u is, it started from rest, that is 0 plus 9.81, then times time, which time is, we have got the time it reaches the beam, which was 0.239 in part 2. So let's find that that velocity. So we have 9.81 times 0.239, which is 2.34. So the velocity with which it arrives at the beam is 2.34 meters per second. So we can now, this is going to be like the initial velocity when it is just crossing the beam. So we can now use S is equal to ut plus a half at squared. So the distance which crosses the beam is now going to be the diameter of the ball, which is going to be 0.08. By the way, this was 0.08. This was 0.08. That's what the one which gives us 0.36. Yes, 0.08. So this is 0.08, which gives us initial velocity now is going to be 2.34. The time is the one we want, plus a half times 9.81 times t squared. So you should be able to solve this quadratic equation if you are a good mathematician. So you will have that 9.81 t squared plus, I'm multiplying this by 2, which will be 4.68 t. I bring 0.08 on the left hand side. After multiplying it by 2, it will be 0.16. This should give us 0. So you should be able to solve that quadratic equation. I hope it is possible for me to solve this here. I'm not good at using this calculator, but let me try. Equation degree 2, that is going to be 3. A is 9.81, B is 4.68, and C is negative 0.16. So that is 0.032. So you are seeing that t is 0.032 when you solve that quadratic equation using a calculator. Okay, so shift. Now the challenge is resetting this calculator. Okay, so we have agreed that the time interval is 0.0332. A different ball is released. A different ball is released from the same position as the steel ball in B. This ball has the same diameter but a much lower density. Same diameter, much lower density. So if it is the same diameter, it means the volume is the same, but the density is less. So it means since mass is equal to density times volume, same volume but lower density, that means it is a smaller mass. It has a smaller weight. So the weight is going to be smaller. State and explain the change, if any, to the time interval during which the beam of light is broken by the ball. Since it is now lighter, it means the effect of air resistance could be greater. So it means the air resistance is going to be greater. Therefore, it is most likely going to take a longer time to reach because of the smaller size. So we are saying, I'm saying because the density is smaller, it means the mass has reduced, and it means the weight is now smaller. So it means the speed of a lower density ball is going to be less because of a greater air resistance. So speed of a low density ball is less. The speed of a low density ball is less, which means the average resultant force or acceleration is less. The average resultant force and thus acceleration is less. And if that is true, it means the time interval is longer. So time interval is longer. Because the air resistance now has a greater effect on the lighter mass, it means it will take a longer period of time. It will take a longer period of time to break the beam, or to break the beam over a long period of time, because for a low density ball, we have seen that its weight is less, which means there is more acceleration. So the average resultant force is going to be less, since when the ball is falling, the air resistance is upwards, the weight is downwards. Because the air resistance is now greater, the average resultant force is going to be less. So it means the time interval during which the beam is broken is going to be greater. So the time interval is longer. Acceleration, define acceleration. We now know that acceleration is the rate of change of velocity. A ball is kicked from horizontal ground towards the top of a vertical wall as shown here. So the ball is kicked at an angle of 28 degrees to the horizontal with a speed v. The ball hits the top of the wall in a time of 1.5 seconds. Air resistance may be assumed negligible. So it means the motion can be considered to be uniformly accelerated motion. Calculate the initial horizontal component Vx of the velocity of the ball. So we want to find the Vx. We shall simply use the equations of motion. S in the horizontal is equal to initial velocity in the horizontal times t plus a half times acceleration in the horizontal times t. If I consider horizontal motion, I want you to note that acceleration in the horizontal is always 0, simply because there is no resultant force in the horizontal. The horizontal distance has been given as 24. We want the initial component, the initial horizontal component, Vx, of the velocity of the ball. So this will be equal to the Vx, that is the velocity of the ball, times the time t, which time is actually 1.5 seconds. So we just divide both sides. So the Vx is going to be 24 divided by 1.5. So that is 24 divided by 1.5, which is 16. So the initial horizontal component is 16. Instead, the initial vertical component, Vy of the ball, show that the initial vertical component is 8.5. So vertical component, the horizontal component that we have found as Vx, which is 16, is the same as V, the velocity V. We resolve V in the horizontal, it is supposed to be V cos 28, and in the vertical, it is supposed to be V sine 28, the vertical component. So the horizontal component, which is 16, is supposed to be V sine 16. I mean sine 28. And the vertical component, which we are calling Vy, is supposed to be V. Sorry. The horizontal component is V cos 28. The vertical component is V sine 28. Remember, I want to find V in the vertical. So I will just divide the two equations. V in the vertical divided by 16 is going to be V sine 28 divided by V cos 28. So V cancels out. The vertical component Vy is going to be 16. Sine 28 over cos 28, as a mathematician, that is tan 28. So you have 16 tan 28, which is going to be 8.507. So this is 8.507, or approximately 8.5 meters per second as required. Calculate the time taken for the ball to reach its maximum height above the ground. Time taken to reach maximum height. So using the equations of motion, V equals to U plus AT. The maximum height is in the vertical, so I'll use V in the vertical, initial velocity in the vertical, acceleration in the vertical. At maximum height, V is 0. At maximum height, V in the vertical at maximum height is 0. So 0 equals to initial velocity in the vertical, we have it as 8.5. So that is 8.5. It is moving against gravity, so acceleration is negative g. So this will be minus 9.81, then times t. So this gives us t as 8.5 divided by 9.81. So 8.5 divided by 9.81, which gives us 0.87. So that time is 0.87. The ball is kicked at time t equals to 0. On the figure, sketch the variation with t of the vertical component Vy of the velocity of the ball until it hits the wall. It may be assumed that the velocity is positive when in the upward direction. So it means since the velocity upwards is positive, our graph will start from the top part. The initial vertical component of velocity at t equals to 0 was 8.5, so our graph will start from 8.5. The scale on the vertical is 5 divided by 10, which is 0.5, so this is 6, 7, 8.5. So 8.5 is here at t equals to 0. Then we have seen that the graph reaches the maximum height at 0.85, and at maximum height V is 0. So we look for 0.87. So the scale on the x-axis is 0.2 divided by 10, which is 0.02. So this is 0.82, 84, 86, 88 is supposed to be here, so 87 is here. This is 0.87. So the graph crosses the x-axis at that point. And remember, the ball takes a time of 1.5 seconds to reach, to hit the wall. So it means our graph will stop at 1.8 seconds. But remember, it is going to change direction. So our graph will continue at 1.5. Let me look for 1.5. The velocity will be now in the opposite direction until it hits the wall. in the opposite direction. So I'm just looking for 1.5 so that my graph stops there. 1, 2, 3, 1, 2, 3, 4, 5. So I think 1.5 is here. So our graph should stop along that point, along that line. So we shall draw a straight line which starts from 8.5. I will increase the thickness. So we shall draw a straight line which starts from 8.5. It goes through 0.87. That's when the graph goes to 0. You can draw a better graph. It is not very easy to sketch on a computer. Okay. Then the graph will continue because there is a change in direction when it is now falling, moving towards the wall. So I'll prolong this graph downwards. So this graph should not go beyond 1.5 because it hits the wall at 1.5. So the graph stops around 1.5 at some value there. If you're very accurate on your sketch, you'll even get that value at which the time at which, the velocity with which it hits the wall. Okay, so that is going to be our graph. That is going to be our graph. It is the most important thing is that it is starting from 0, t equals to 0 and 8.5. Then it crosses the x-axis at 0.87 when v becomes 0. And I'm saying it does not go beyond 1.5 because it hits the wall at 1.5 seconds. So the graph does not go beyond 1.5. It continues in the negative part because when the body is falling, it is now moving in the opposite direction. It is moving downwards before it hits the wall. So you see it moves to the maximum height somewhere here, and then it now moves downwards before it hits the wall. So use the information in B to determine the maximum height of the ball. Information in B to determine the maximum height of the ball. Okay, so in B, we could use the equations of motion such as v squared equals to u squared plus 2as because we want to find the maximum height. Since at maximum height v is 0, we shall say v squared is equal to the initial velocity that we got in B in the vertical. Remember, maximum height is in the vertical, so we are dealing with the vertical quantities. So v squared is going to be 0 squared. Initial velocity in the vertical was 8.5, but is squared minus, because it was moving against gravity, 2 times 9.81, then times the h, or the maximum height h. So it means h is going to be equal to 8.5 squared divided by 2 times 9.81. So 8.5 squared divided by 2 times 9.81. So that gives us 3.68 or approximately 3.7. Alternatively, you could use another equation of motion. You could use another equation of motion such as, let me see another one. We could use S equals to ut plus a half at squared. S will be our height. Initial velocity in the vertical is 8.5 as we have already seen. The time taken to reach maximum height, we have calculated it above as 0.87. Then this will be plus or minus because acceleration is going to be negative since it is moving upwards. So that will be minus a half times 9.81. then times the time, which is 0.87, but this is squared. So we can check again. We can check again using a calculator. So 8.5 times 0.87 minus 0.5 times 9.81 times 0.87 squared. So we see it is the same answer. So this is method 2. So we are saying it is still 3.7. Or by the way, you could use the graph you have just drawn and find the area under the graph. Maximum height is going to be just this area here. You can use the area under the graph. So I will write that method here. The maximum height h is going to be called the area under the graph. Area under the graph, which is going to be a half times the base will be maybe 0.87 times the height, which will be 8.5 maybe. That is area under the graph. So this is going to be a half, which is 0.5 times 0.87, which is the base, times 8.5, which gives us again 3.7 meters. So we could use any of those methods to find the maximum height. Okay, the maximum gravitational potential energy of the ball above the ground is 22 joules. Calculate the mass of the ball. So we know that maximum gravitational potential energy is mgh. Potential energy is mgh. So the change in gravitational potential energy is going to be mg times the change in the height h. So they have given us that this is 22 is equal to the m, which we want to find, times g, which is 9.81, times the maximum height, which we have seen as 3.69 or 3.7. So to find m, we just divide. M will be equal to 22 divided by 9.81 times 3.7. So we have 22 divided by 9.81 times 3.7. So that is 0.606, which is 0.61. 0.61. A ball of greater mass is kicked with the same velocity as the ball in B. Greater mass. State and explain the effect, if any, on the increased mass on the maximum height reached by the ball. Air resistance is still assumed to be negligible. So the ball is now of a larger mass, and it means the weight W downwards has increased. But the air resistance is still negligible. It is kicked with the same velocity v, and we notice that what is contributing to the maximum height, when you look at the formula v squared, for example, equals u squared plus 2as, there is no mass in it. Any equation of which is contributing to the time, any equation which is contributing to the height does not have mass in it, because the acceleration is not going to be changing, because the acceleration is not going to depend on the mass. So it means there is no effect of changing the mass, because the acceleration of free fall remains constant since it is not dependent on the mass. So we are simply going to say no effect. No effect on the maximum height. There is no effect on maximum height. Reason: acceleration is not changed. Acceleration of free fall is not change. It does not change. Acceleration of free fall or acceleration due to gravity. Acceleration of free fall is unchanged since it is not dependent on mass. Since the acceleration of free fall does not depend on mass and it is the one determining, it is actually the one because maximum velocity is going to be 0 at maximum height. Initial velocity is the same, so we want h. H is only being determined by A, yet A is not dependent on the mass, so there will be no effect on the maximum height because the acceleration of free fall does not change since it is not dependent on the mass. Define velocity. We now know that velocity is the rate of change of displacement. Rate of change of displacement, that is velocity. Rate of change of displacement, that is velocity. A car travels in a straight line up a slope as shown in the figure here. So we can look at the figure. So the mass is 850 kilograms and the speed is constant. It is moving with a constant speed. That means there's no resultant force on the car. The acceleration is 0. The car's engine exerts a force on the car of 2 kilonewtons up the slope. A resistive force Fd due to friction and air resistance opposes the motion. So there is the force, which is 2 kilonewtons, that is by the car's engine, that is 2 kilonewtons. And then there is a resistive force which we are calling Fd, which opposes the motion of the car. The variation of Fd with the speed, v of the car is shown in the figure. So here we have variation of the resistive force with the speed, and we see that the resistive force is increasing with the speed. Okay. State and explain whether the car is in equilibrium as it moves up the slope. Because they said it is moving with a constant velocity, then the resultant force is 0. So the car is in what we may call dynamic equilibrium. So we can say with a constant velocity, the resultant force is 0. With a constant velocity, the resultant force is 0, so the car is in dynamic equilibrium. So when a body is moving but at a constant velocity, we say it is in dynamic equilibrium because the resultant force is going to be 0. Consider the forces that act along the slope. Use data from the figure to determine the component of the weight of the car that acts down the slope. We want the component of the weight of the car that acts down the slope. Component of the weight of the car that acts down the slope. So when we look at the graph, when we look at the figure here, the car has a mass of 850 and travels with a constant speed of 9 meters per second. So let's look for a speed of 9 meters per second. So 9 meters per second is correspond to 0.4 newtons. That is actually the resistive force. Remember, the resistive force combines air resistance and friction. Yet when we come here, there is a component of the weight. Let's say this is the weight W. weight W has a component perpendicular to the plane, which would be W cos of theta if there was an angle theta here, and there's a component of W down the plane, which would be W sine theta. And so we want this component down the slope. So the component down the slope plus the frictional force down the slope should be equal to the force upwards, because the resultant force is 0. Should be equal to the force upwards. The component of the weight down the slope plus the resistive forces, that is friction plus air resistance or another resistive force, Fd down the slope, should give us the force upwards, because the resultant force must be 0. So I will simply write this so that the component of the weight down the slope plus the resistive forces plus friction should be equal to the force of the car, engine, simply because the resultant force is equal to 0 because the velocity is constant. So the component of the weight will therefore be equal to the force of the car engine minus Fd. So the component equals to the force of the car, which is 2 kilonewtons, that is 2 times 10 power 3, minus the Fd at 9 meters per second, it is 0.4 times 10 power 3. So this is 0.4 times 10 power 3. And we can check this. 2 minus 0.4 is actually 1.6 times 10 power 3. So this is 1.6 times 10 power 3. Show that the power output of the car is 1.8 times 10 power 4. We know that power is work done over time taken, which gives us force times velocity. So power is going to be the force of the car, which is 2.0 times 10 power 3, times the velocity, which is 9. That means the power is going to be 2 times 9, which is, I think, 1.18. Okay, 2 exponent 3 times 9. That is 1,800, which is 1.8. I mean 18,000, which is 1.8 times 10 power 4 watts. The car now travels along a horizontal ground. The output power of the car is maintained at 1.8 times 10 power 4. The variation of the resistive force Fd acting on the car is given in the figure 3.2. So it means we are using the same figure for the resistive force, the variation of the resistive force with time. Calculate the acceleration of the car when its speed is 15 meters per second. So first of all, the power of the car has remained the same, and secondly, the speed is 15 meters per second. So we can find the driving force of the car. This time, the force of the car at that speed is going to be 1.8 times 10 power 4 divided by 15. So this gives us the force of the car, or the driving force. So that one divided by 15, so that's 1.2 times 10 power 3 newtons. That is the force of the car. So the variation of the resistive force Fd acting on the car is given by figure 3.2. We want to find the acceleration of the car. Find the acceleration, we must now find the resultant force. If the car is still moving, if the car is moving forward, it means the force of the car is greater than the resistive force. So the resultant force, F resultant, I'll put Fr, should be equal to the force of the car minus Fd, that is the resistive force. So the resultant force is going to be the force of the car, which is 1.2 times 10 power 3 minus FD. At 15 meters per second, what is FD? At 15 meters per second, 15 meters per second, 15 meters per second, FD is, I think this is, the scale on the vertical is 0.4 minus 0.3, that is 1. So the scale on the vertical is 0.01. So 61, 62, 63, 64, 65, 66. So that is 0.66. So FD is 0.66 times 10 power 3. So this is 0.66 times 10 power 3. Remember, resultant force F is mass times acceleration. The resultant force is mass times acceleration. So acceleration is going to be the difference. 1.2 times 10 power 3 minus 0.66 times 10 power 3 divided by the mass. And the mass of the car was 850, I guess. It is 850. So 1200 minus, open bracket, 0.66 exponent 3 divided by 850. So that is 0.635 or 0.64. 0.64. Complete the figure to indicate whether each of the quantities is a vector or a scalar. Now we know the scalars and we know the vectors. So if we know the vectors, we know the scalars. So here we see it is only acceleration, which is a vector. I say there are 6 vectors: acceleration, displacement, velocity. We have momentum or impulse. We have force or weight, and we have moment or torque. So speed is a scalar. Power will be a scalar. A ball is projected with a horizontal velocity of 1.1 meter per second from point A at the edge of the table as shown here. Okay, so we have the horizontal distance 0.43, the speed is 1.1. The ball lands on a horizontal ground at point B, which is a distance 0.43 from the base. Air resistance is negligible, so we can use acceleration as 9.81 because it will be constant. Calculate the time taken for the ball to move from A to B. So since we have velocity in the horizontal and we have displacement in the horizontal, we can consider horizontal motion. So considering horizontal motion and using S equals to UT plus a half AT squared. S we shall consider in the X, initial velocity in the X, acceleration in the X. Remember, acceleration in the horizontal is 0 because there is no resultant force in the horizontal. Therefore, this part will be 0. S in the X is given as 0.43. Initial velocity in the horizontal is 1.1, then times the time t. So we now find t by dividing both sides. 0.43 divided by 1.1. 0.43 divided by 1.1, that is 39 point, let me check, 0.43 divided by 1.1, 0.43 divided by 1.1. Okay, that is 0.39. So this is 0.39. Use your answer in B Roman 1 to determine the height of the table. Use your answer in B Roman 1 to determine the height of the table. So we want the vertical distance. So we need to use vertical motion. So S in the vertical is equal to initial velocity in the vertical times t plus acceleration in the vertical, a half acceleration in the vertical times t squared. So here we have an acceleration in the vertical, but the body is falling, so we can't put the negative. So we want the height h, which is s in the vertical. Initial velocity in the vertical is 0 because the body was projected horizontally. So initial velocity in the vertical is 0. So we are saying initial velocity in the vertical is 0 because the body was projected horizontally. So h is going to be a half times a, which is 9.81, times the time is the same because time is a scalar quantity, so this will be 0.39, and that is squared. 0.5 times 9.81 times 0.39, and it is squared. That is 0.746 or 0.75. The ball leaves the table at time t equals to 0. For the motion of the ball between A and B, sketch graphs on the figure to show the variation with the time t of the acceleration A of the ball. We have seen first of all that the acceleration is constant if air resistance is negligible. So it means the graph will just be a horizontal line to show constant acceleration with the time. So this will be a horizontal line for acceleration. Then the vertical component SV of the displacement of the ball from A to B. The vertical component, of course, the vertical component is actually increasing. The vertical component of the displacement, initially the displacement is 0 before it falls, but the vertical component increases. In fact, because v squared is equal to u squared plus 2as, as the ball falls, v increases. This one increases. Therefore, the vertical component s increases rapidly since initial velocity is 0. So it means the graph is going to be a graph of an increasing gradient because the velocity increases rapidly as time goes on. When the body is falling, the speed increases. So the graph must be having a gradient which is increasing. How do I show that the velocity is increasing as the ball moves? So this graph should be curving upwards to show an increasing gradient. So at t equals to 0, s is 0. Then the graph goes upwards to show that the gradient is increasing with the time. So the curved line which starts from the origin should have an increasing gradient because the velocity is increasing. The velocity increases with the time. So that will be the graph. Remember, the gradient of displacement time graph is the velocity. A ball of a greater mass. A ball of a greater mass is projected from the table with the same velocity as the ball in B. Air resistance is still negligible. That is very important. If air resistance is still negligible, then the acceleration is still g. State and explain the effect, if any, of the increased mass on the time taken for the ball to fall to the ground. If air resistance is still negligible, then the mass has no effect because acceleration of free fall is not going to be changed since it is not dependent on the mass. So we are saying there is no effect on time taken since or because acceleration of free fall is unchanged. Since it is not dependent on mass, so it is unchanged. Okay, so there is no effect because the acceleration of free fall does not change because it does not depend on the mass. Okay. Define the following displacement. We know displacement is distance in a specified direction from a point. So that is distance moved. Distance moved in a specified direction. In a specified direction from a point. By the way, displacement is actually the shortest distance between 2 points. That is displacement, the shortest distance, or the straight line distance between 2 points. Straight line distance between 2 points. That is displacement. And acceleration, we know that acceleration is the rate of change of velocity. That is acceleration, rate of change of velocity. A man wearing a wingsuit glides through the air with a constant velocity of 47 meters per second at an angle of 24 degrees to the horizontal. The path of the man is shown in the figure. The total mass of the man and the wingsuit is 85 kilograms. The man takes a time of 2.8 minutes to glide from point A to point B. So the time from A to B is 2.8 minutes. With reference to the motion of the man, state and explain whether he is in equilibrium. Of course, they mentioned constant velocity. So constant velocity means the resultant force is 0. So with constant velocity, resultant force is 0. So he is in equilibrium. So the man is in equilibrium. So with a constant velocity, it means the resultant force is 0. So the man is in equilibrium. Show that the difference in height h between points A and B is 3,200. Difference in height h. So first of all, we can find the distance AB. Because the speed is constant, the distance AB is going to be speed times time, since the speed is constant. So distance AB is going to be the speed times time, because the speed is constant. So the speed was 47 meters per second, and the time between A and B was 2.8 minutes, which is 2.8 times 60 to change it to seconds. So that is the distance AB. So we now know distance AB, and we want h. H is in the opposite, distance AB is in the hypotenuse. So we shall use sine. Sine of 24 is equal to the opposite over the length AB. So sine 24 is equal to the opposite, which is h, over the distance AB, which means that h is equal to the distance AB times sine 24, which will be the distance AB, which we have seen as 47 times 2.8 times 60 sine of 24. So let's check. 47 times 2.8 times 60 sine of 24. So we have 3211. So this is 3211, which is approximately 3200 meters. So we have now that this distance is 3200 meters. No, we have that the height is 3200 meters, not this one. Okay. For the movement of the man from A to B, determine the decrease in gravitational potential energy. Remember, when we are finding potential energy, we look at only the vertical height. Decrease in gravitational potential energy. For potential energy, we only look at the vertical height. Therefore, the decrease in potential energy, which is delta AEP, is going to be equal to mg times the change in height. So since they gave us the mass as 85, g is 9.81, the height we have seen is 3,200. So just find the decrease in potential energy as 85, 9.81, 3,200. which is 266. So I'll write 2.67 times 10 power 6 times 10 power 6. So this is 2.67 times 10 power 6. That is the decrease in gravitational potential energy. Then the magnitude of the force on the man due to air resistance. Remember, there is no change in kinetic energy from A to B. So that means if there is no change in kinetic energy, so change in speed is equal to 0, which means change in kinetic energy is equal to 0. So it means the decrease in gravitational potential energy must be equal to the work done against air resistance, because the only force acting here is air resistance. So the work done against air resistance must be equal to the decrease in gravitational potential energy, because the man is moving with a constant velocity. So the work done against air resistance is going to be equal to the decrease in gravitational potential energy. Since there is no change in velocity, and that means there is no change in kinetic energy. Remember, work done is force times distance. So the friction, the force due to air resistance, I'm calling it Fr, times the distance s is equal to the decrease in gravitational potential energy, which is 2.67 times 10 power 6. So the frictional force is going to be equal to 2.67 times 10 power 6 divided by the distance. Now the distance is along the path, it is not the vertical height. Whenever we are finding the work done against resistance, we consider the distance AB, where we have seen AB is the speed, 47, times time, which is 2.8, times 60 to change it to seconds. So this will be divided by 47 times 2.8 times 60 to change it to seconds. So the friction force, or the force due to air resistance, is going to be that answer, 2.67 exponent 6 divided by 47 times 2.8 times 60. So that is 338, which is approximately 340. So this is 338, which is approximately 340 newtons. The pressure of the steel air at A is 63 kilopascals and at B is 92 kilopascals. Assume that the density of the air is constant between A and B. Determine the density of air between A and B. So we have seen that the pressure at A is this, pressure at B is that, and we know that the change in pressure, or difference in pressure, is equal to density times G times difference in height h. We want the density. So the density is going to be the difference in pressure divided by G times the difference in height h. The difference in pressure is 92 minus 63, it is kilo, so that is times 10 power 3, divided by G, which is 9.81, times the change in height, which height was 3,200. So we can find this, 92 minus 63, okay, let me say 92 minus 63 exponent 3. What is that? 92 exponent 3 minus 63 exponent 3. Then divide by 9.81 times 3,200. So that is 0.923. 0.923. So the density is 0.923 kilograms per meters cubed. Okay. A dolphin is swimming underwater at a constant speed. It is at a constant speed. The dolphin emits sound as it swims directed towards a stationary observer. So it is towards. The frequency of the sound heard by the driver is 9560. the speed of sound in the water is 1510 meters per second. Determine the frequency to three significant figures of the sound emitted by the dolphin. Because it is towards, the observed frequency is higher, so this will be F is going to be equal to V over V. So this will be minus because the observed frequency is higher. We subtract the speed of the source, then times F. If it was away, we would add, we would say V over V plus. So the observed frequency is 9560 is equal to the frequency of the source we don't know, then times 1510, which is the speed, divided by 1510 minus the speed of the dolphin, which is 4.2. I mean 4.5. So this should be able to give us Fs. So we just cross multiply. We shall just cross multiply 9560 times open brackets 1510 minus 4.5 then divide by 1510. Because they wanted to three significant figures, that would be 9530. So Fs is equal to 9531, which is approximately 9530. The dolphin strikes the bottom of a floating ball so that the ball rises vertically upwards from the surface of the water. The ball leaves the water surface at a speed of 5.6 meters per second, assuming air resistance is negligible. Calculate the maximum height reached by the ball above the surface of the water. Air resistance is negligible, so equations of motion can apply because the acceleration is going to be constant. Therefore, we can use v squared equals to u squared plus 2as because we want maximum height. When it reaches the maximum height, v is 0. So we shall say 0 equals to initial velocity is 5.6 squared minus, because it was moving upwards, 2 times 9.81 times the maximum height h. So h is equal to 5.6 squared divided by 2 times 9.81. 5.6 squared divided by 2 times 9.81. So that is 1.598. 1.598, which is approximately 1.6 meters. So that is going to be the maximum height. The ball leaves the water at time t equals to 0 and reaches its maximum height at time t equals to capital T. Sketch a graph to show the variation of the speed of the ball with t from t equals to 0 to t equals to t. Numerical values are not required. Because at maximum height v is 0, so the graph will reach 0. It started with a value of 9.6, so the graph starts from a non-zero value. As it's moving upwards, the velocity decreases. Since air resistance is negligible, acceleration is constant, or it is going to be a negative deceleration, negative 9.81. So the graph will have a negative gradient because the body is moving upwards, but this is a constant acceleration, so it will be a straight line. Because a straight line means a constant gradient, which is a constant acceleration, a speed time graph. So we shall have a graph which is a straight line from a non-zero value to t. The graph starts from a non-zero value of speed to t and is a straight line, starting from a point on the speed axis and ending at a point set t0, or on the x-axis the value of t is capital T and the value of speed is 0 because it comes to the maximum height where speed is 0. The mass of the ball is 0.45 kilograms. Use your answer in B Roman 1, which is the vertical height, to calculate the change in gravitational potential energy of the ball as it rises. We want change in gravitational potential energy. So change in gravitational potential energy is equal to mg times the change in the height h. So the mass is 0.45, g is 9.81, and the height is 1.6, as we have calculated in part 1. So 0.45 times 9.81 times 1.6, and that gives us 7.06, or approximately 7.1 joules. State and explain the variation in the magnitude of the acceleration of the ball as it falls back towards the surface of the water if air resistance is not negligible. When it is falling, the speed is increasing. And if it is falling, now it is falling downwards. There is a weight downwards. Motion is downwards. The force due to air resistance will be upwards. Force due to air resistance is upwards. When it is falling, the weight is constant. The force due to air resistance upwards increases, since when it is falling, the speed is increasing. This means the resultant force on the ball, which will be the weight minus the force due to air resistance, will decrease because air resistance is increasing. If the resultant force increases, the difference between the weight and the resultant force decreases, which means the resultant force decreases. If the force due to air resistance increases, the difference between the weight and the force due to air resistance decreases, which means the resultant force decreases. But remember, the resultant force is mass times acceleration. If the resultant force is decreasing, it means the acceleration is decreasing. Therefore, the acceleration decreases because we want the magnitude of the acceleration. So the acceleration is going to decrease in magnitude. So we are saying as it falls, speed increases, so air resistance increases. As it falls, speed increases, so air resistance increases, because air resistance increases with the speed. Let me just say air resistance increases with the speed. As it falls, speed increases and air resistance increases with the speed. Air resistance increases with the speed. Since the weight is constant, because the weight is constant, the resultant force decreases. The resultant force decreases, hence acceleration decreases. Yeah, so since the weight does not change, but the air resistance upwards is increasing, so the difference between the weight and the air resistance becomes smaller. That difference is the resultant force, and the resultant force is directly proportional to acceleration. So if the resultant force decreases, the acceleration decreases. An experiment is conducted on the surface of a planet Mars. A sphere of mass 0.78 kilograms is projected almost vertically upwards, from the surface of the planet. The variation with the time t of the vertical velocity v in the upward direction is shown in the figure. Okay, So the graph here, it is moving upwards. When the velocity is 0, it has reached maximum height at this point here, which is going to be 2.1234. That is at 2.4, it is at maximum height. The sphere lands on the small hill at t equals to 4 seconds. State the time t at which the sphere reaches its maximum height above the planet's surface. So we have seen from the graph that is automatically 2.4. So it reaches maximum height when v equals 0. V must be equal to 0 at maximum height. And from the graph, you see v is 0 at t equals 2.4. Determine the vertical height above the point of projection at which the sphere finally comes to rest on the hill. We want the vertical height, so that we can simply find the area under the graph, or we can even use equations of motion. We can use equations of motion, but I'll begin with the simplest, area under the graph. So distance or height will be equal to the area under the line, but that is between t equals to 0 to t equals to 2.4. Oh, sorry. We want the vertical height above the point of projection at which the sphere finally comes to rest, or finally lands. Okay. So we shall need, remember it is moving upwards, it moves upwards, it reaches maximum height, then it falls downwards. We see that the area up above, when it is going above, is greater than the area when it is coming below. So it means it doesn't reach back, it doesn't reach at the same point. So this is the distance we want. That distance here. It starts from here, reaches maximum height, and it comes to rest at a hill. So we want this vertical distance here. So going upwards, it is represented by the first area up to 2.4. Coming downwards is represented by the second area from 2.4 to 4. So we want this remaining part, so we shall subtract those distances. So distance will be area under the line, which will be, for the first one is a triangle, which is a half. The base is maybe 2.4 times the vertical, which is the vertical is 9 point, I think that is 9, because the scale on the vertical is 5/10, which is 0.5. So that one is 9. So this will be times 9.0. Then minus the other area, which will also be a half, times the base, which is from 4 to 1. We have 4 minus 2.4, which is 1.6. So times 1.6. Then on the vertical, we have this one here, which is 5, 6. So that is 6, negative 6. So this will be times 6. So now simply press our calculator. A half is 0.5. I will just put in the brackets 0.5 times 2.4 times 9 minus 0.5 times 1.6 times 6, which is giving us 6.0. So this is 6.0 meters. So the height is 6.0 meters. Method 2, we could also use the equations of motion. We could use the equations of motion in method 2. I could use S equals to ut plus a half at squared. So I want S. Initial velocity was 9 from the graph, 9.0 times the time. The time is 4. To reach the hill is 4. But initial motion was upwards, so the acceleration is going to be negative. So this will be minus a half times. Now we have to find this acceleration here, which is going to be the gradient. The acceleration is going to be the gradient. I can just take a small part of the gradient. The acceleration will be 9 minus 0, which is 9, divided by 2.4 minus 0, which is 2.4. That can be the acceleration. So I will multiply this by a, which is 9 over 2.4. I've put a negative because the object was moving in the opposite direction to the gravity on that planet, then times the time. The total time, of course, is 4 squared. So we can check this also and see what we get. So we have 9 times 4 minus, open brackets, 0.4, 0.5, that is a half, times 4 squared, then times, open another bracket, 9 divided by 2.4. So I close the brackets. So you see it gives me 6. So that is 6 meters. Okay, any other method that you think can lead you to 6 meters is fine. Calculate for the first 3.5 seconds of the motion of the sphere the change in momentum of the sphere. So we want to find the change in momentum of the sphere for the first 3.5 seconds. Let's look for 3.5 seconds. So this is 3.1, 2, 3, 4, 5. So this is 3.5 and the speed is here. I think this speed is, let me see, the speed is here in the box. So the scale on the vertical is 0.5, 0.5. This is 1, 2, 3, 4. It's around 4.2. It is closer to the upper part, so it is 4.2, negative 4.2. It may not be negative 4.5. Because each small square is 0.5, it could be negative 4.2, negative 4.3, around there. Okay? So calculate for the first 3.5 seconds of the motion of the sphere, the change in momentum. So change in momentum, remember momentum is mass times velocity. Change in momentum is going to be equal to the mass, which is 0.78 kilograms, times the change in velocity, which we started from 9.0 up to negative 4.2. So it is minus negative 4.2. So we see 0.78 times 9 plus 4.2. So the momentum is 10.296, which is 10.3. Then the force acting on the sphere, of course, force is the rate of change of momentum. So the force is equal to the change in momentum with the time, or over change in time. So the momentum is 10.3, and the time, of course, the time is 3.5. So this is going to be divided by 3.5, which gives us 2.9. So the force is 2.9 newtons. Use your answer in C Roman 2. Using your answer in C Roman 2, state the weight of the sphere. Since air resistance was negligible, the resultant force is only the force due to gravity. So since, I'll just say air resistance was negligible. Air resistance is negligible. If air resistance is negligible, if air resistance is negligible, resistance is negligible, then it means the resultant force is only the weight. So remember, force, the resultant force is the rate of change of momentum. So it means the weight is going to be simply 2.9. If there's no air resistance, then the resultant force is equal to the weight, or the force, the force of gravity on the planet is simply the weight. Determine the acceleration of free fall on the surface of Mars. Acceleration of free fall. So we know that the weight is equal to mg. That means g is going to be the weight, which is 2.9 divided by the mass, which is 0.78. So 2.9 divided by 0.78, that gives us 3.77. Let me say 2.9 divided by 0.78, that is 3.71. So G is 3.71, or approximately 3.7 meters per second squared. Okay. Complete the figure to show whether each quantity listed is a vector or a scalar. You should now be contemplating about what a scalar is and what a vector is. So distance moved, of course, distance is a scalar. Speed is a scalar. It is only acceleration which is a vector quantity. A ball falls vertically in air from rest. The variation with the time t of distance d moved by the ball is shown in the figure here. So this is distance against time. That's what we are having. Let me minimize it slightly so it fits on the same page. So that is the graph for distance against time. As the ball falls, it falls in air from rest. So initial velocity is 0. Okay. So by reference to the figure, explain how it can be deducted that the ball is initially at rest. So this is a graph of distance against time, and the gradient is the velocity. At t equals to 0, you see that the graph is almost horizontal. The graph is almost horizontal. It means the gradient here is 0. Therefore, if the initial velocity is 0, then it means that the the ball was initially at rest. It was not moving. Because any object which is not moving has no speed. So we can simply say the initial gradient is 0. Initial gradient is 0. Initial gradient is 0. And remember, the gradient of the graph is the speed. Initial gradient is 0, and the gradient is the speed. And the gradient is the speed. The gradient of the graph is the speed. And the gradient of the graph is the speed. So it is at rest. So it is initially at rest. Because the initial gradient is 0, and yet the gradient of the graph is the speed, it means it is initially at rest. Air resistance is not negligible. By reference to the figure, explain how it can be deduced that air resistance is not negligible. So you see that as time goes on, the gradient of the graph increases and then it becomes constant, which means the speed increases and then it becomes constant. So the gradient of the line later becomes constant. So that means air resistance acts. When it becomes constant, the speed is constant, we have reached terminal speed or terminal velocity. So we can say the gradient of the line becomes constant. So the gradient becomes constant at around 0.8 seconds. The gradient of the line becomes constant at around 0.8 seconds. It now becomes a straight line. Use the figure to determine the speed of the ball at time t equals to a time of 0.4 seconds after it has been released. The speed at a time of 0.4 seconds after it has been released. So remember, the gradient is the speed. So I'm now just going to draw a tangent at 0.4 seconds. So I'm going to draw a tangent at 0.4 seconds. So I'm putting there my ruler to draw a tangent. So I've tried to draw a tangent. I don't know whether it is very accurate, but you can draw a better one. I'm aiming at this point and that point there. So I can now find a gradient because the speed is the gradient. The speed is actually the gradient. So this is on the x-axis, this is 0.2. On the y-axis, this is, but the line is very far. Okay, I'll take this point. On the y-axis, this is 0.9. On the x-axis, this is 0.28. And this one is 0.52. So now I'm finding the gradient. So the speed is equal to the gradient at 0.4, which is going to be equal to 0.9 minus 0.2 on the vertical, divided by 0.52 minus, is it 0.52? 1, 2, 3, 4, 5, that is 0.5. So it is 0.52 on the x minus 0.28. So I check 0.9 minus 0.2 divided by 0.52 minus 0.28. So that gives me 2.916, which is 2.92 or 2.9. So that is 2.9 meters per second as the speed. Then on the figure, sketch the graph to show the variation with the time t of the distance d moved by the ball for a negligible air resistance. When there is no air resistance, you are not expected to carry out any further calculations. So when there is no air resistance, first of all, the graph will be above this one. It will never become a straight line. It will never become a straight line. So for negligible air resistance, we shall just draw a continuous curve, which will never become a straight line, because if it becomes a straight line, it means that at some point the velocity became constant because there was air resistance. But this one, the velocity should continue increasing indefinitely. Okay, I'm going to try and sketch this. It is not easy, but I'll try my level best. So the graph will start from the same point, but will always be above this one. Okay, so that is the graph. It will never be, you just ensure that it does not become a straight line. It is a curve which does not become a straight line. It is always going to be above the one that is already there. It is always going to be above the one which is already there because there is no air resistance. And I am saying this curve should be going upwards, meaning the speed continues to increase indefinitely. So you can draw a better curve than mine. It will never become a straight line. So Where you see that I've drawn as if it is a straight line, then that is a mistake. It is not, it will never become a straight line. So that is the curve. It is going to be a continuous curve going vertically upwards, which will never become a straight line. So that is going to be the graph for the variation of displacement against time when air resistance is negligible. The distance s moved by an object in a time t may be expressed in may be given by this expression here: s is equal to a half at squared, where a is the acceleration of the object. State two conditions for this expression to apply. So your teacher must have told you that this is part of an equation of motion, which is actually s is equal to ut plus a half at squared, meaning that the initial velocity was 0. That means that's how we came up with this expression here. And this expression only applies for uniformly accelerated motion. So the first condition that applies for this expression is that the initial speed is 0. Initial speed is 0. The second condition, to use this equation, the acceleration must be uniform. So the acceleration is constant. The acceleration is constant. And of course, normally when we use these equations, we are referring to uniformly accelerated motion, which must be motion in a straight line. So we can say the motion is in a straight line. The motion is in a straight line. The motion is in a straight line. A student takes a photograph of a steel ball of radius 5 centimeters as it falls from. The radius of the ball is 5 centimeters. That means the diameter is 10 centimeters. The image is blurred because the ball is moving while the photograph is being taken. So we are seeing the initial position of the ball in the photograph and the final position of the ball in the photograph. So we can first think of the boundaries on top. I think on top this is along that is 7.9, I guess. At the bottom, I think the bottom is at around 89. This is 89. And this is 79, not 7.9. That is 79. This is 89. Okay, then here, the final position of the photograph at the bottom. I think at the bottom here it is at 100. That is at 100. Okay, let's see the question. The scale shows the distance. The scale shows the distance from rest by the ball, falling from rest by the ball. At equals to 0, the top of the ball is level with a 0 mark. But here we have not seen, they have not showed us the 0 mark. But at equals to 0, it is at the 0 mark. Air resistance is negligible, meaning equations of motion can now apply. Calculate an appropriate number of significant figures. The time the ball falls before the photograph is taken. The photograph is taken when the ball is, it has covered a distance of 79 centimeters. So we now want, because remember t was 0, because it was falling on a 0 mark. At t equals 0, the ball was at the 0 mark. So it means the photograph is taken when it is at 79 centimeters. So using the equation above, s is equal to ut plus a half at squared, which gave us a half at squared alone. 79 centimeters, that is 0.79. So 0.79 is equal to a half times the acceleration, which is 9.81, then times t squared. So t is going to be 2 times 0.79 divided by 9.81 under the square root. So t is going to be the square root of 2 times 0.79 divided by 9.81. So that gives us 0.40 seconds. Then the time interval during which the photograph is taken. The time interval during which the photograph is taken. So what is the distance traveled by the end of this time interval when the photograph is taken? So we have the initial position of the ball in the photograph, and we are seeing the final position of the ball in the photograph, which is I think from 79, I think this is at 90. That is at 90 centimeters. So the distance traveled by the end of the time interval, I think it is 90. The starting interval is at 79, then it is at 90 centimeters. So distance traveled by the end of the time interval is 90 centimeters. Distance traveled by the end of time interval. The distance traveled by the end of the time interval, it will be now at 90 centimeters. So we can find the time it reaches 90 centimeters using the same formula above. S is equal to a half, 80 squared. So 0.9 is equal to a half times acceleration, which is 9.81, then times t squared. So we can find it t again as the square root of 2 times 0.90 divided by 9.81. So square root of 2 times 0.9 divided by 9.81. So that is 0.43. So this time is 0.43. The time the ball falls before the photograph is taken is 0.4, and the time or the distance traveled, I mean the time at the end of the photograph, or at the end of the time interval, is 0.43. So it means the time interval we are looking for is actually going to be 0.43. That is at the end of the photograph minus 0.40 when the photograph is being taken, which gives us 0.03 seconds. That is the time interval during which the photograph is taken. The student in B takes a second photograph, starting at the same position on the scale. The ball has the same radius but less density. Same radius, less density. Because it is less dense, mass is equal to density times volume. Same radius, same volume. Weight of the ball is going to be density times volume times g. That is mass times g. Same density, same radius, that means same volume. Less density, smaller density means the less weight. If it is same volume, it means same surface area. It means the same air resistance acts. They're saying air resistance is not negligible. But since the weight, the density has become smaller, the weight has reduced. State and explain the changes that will occur in the photograph. Since now the air resistance is not negligible and the density is less, meaning the weight is less, it means the air resistance is going to be greater now. And the air resistance will reduce the motion of the ball. That means the time interval is going to be actually, it means the time interval is going to be shorter because state and explain the changes that will occur on the photograph. It means the length of the image is going to be shorter this time, simply because there is air resistance. It means by the time the photograph is taken, the image, I mean the ball has not traveled a longer distance. It means the length of the image is going to be shorter because there is air resistance which slows down the ball. It means by the time the image is taken, it means the length of the image is going to be shorter since the air resistance reduces the speed of the ball. So we are saying presence of air resistance means the ball's speed, the ball's speed, the ball's speed, or let's say the acceleration. The ball's speed or acceleration is less. That means if the speed is small, it means you will take the photograph, and it means the length of the photograph will be shorter. So the length of the photograph, the length of the image is shorter. So if we take the image in the same time interval, for example, yet is now moving slower. It is moving slowly. The ball is moving slowly because of air resistance. Then it means the length of the image is going to be shorter because the presence of air resistance means that the ball's speed or acceleration has reduced. Okay. A cyclist is moving up a slope that has a constant gradient. The cyclist takes 8 seconds to climb. So the slope is taking 8 seconds to climb the slope as shown with the velocity time graph. Okay. Use the figure to determine the total distance moved up the slope. Now this is another example where the graph is not a perfect straight line, that we have to find its distance. So distance is equal to the area under the graph. Distance is equal to the area under the graph. So me, I would prefer to first of all get a rectangle from this graph. I would first get a rectangle from the graph. So I'm drawing a rectangle. So that is a rectangle. So I'll find the area of the rectangle, which is going to be 8 times 6. So this will be 8 times 6. That is for the rectangle. Now I will subtract the other part outside, below the above the graph. So I can draw a tangent here. I'll draw a graph. I will draw a tangent or a line here, which removes a triangle. That is not good enough. Okay, so I'm removing that area of that triangle. So the triangle is stopping around here. I'm just going to estimate it to that point. So this is, and I think that is 2 point, because the scale is 0.2, so that is 2.6 on the vertical, and then here on the vertical, so that is on the x-axis. Then here we have, I think this is 1, 2, 3, 4, 5. I think that is 3. So the area of that triangle is going to be a half base times height. So this will be 3, and this is approximately 6. So I'll say a half times 6 minus 3, which is 3, times the base, which is 8, and 2.6, which is 8 minus 2.6, which is 5.4. So that will be times 5.4. That is the area of the triangle, but I'm also going to subtract the area of the remaining part which is not part of the triangle, where I'm going to just count the squares. So I'll say plus. Let me first get the area of one small square. So one small square is equal to, on the x-axis it is 2 divided by 10, which is 0.2. On the y-axis it is 2 divided by 10, which is 0.2, meaning one small square has area of 0.04 in meters. So let's see how many small squares are not part of the triangle. The full squares, we have 1, 2, 3, 4. Okay, let me start from here. 1, 2, 3, 4, 5, 6, 7, 8, 9. I've counted approximately 9 small squares. So for the full squares, I will say plus. The area of the full squares will be 9 times 0.04. Plus, for the half squares, I will say a half times the area of one full square, then times the number of half squares. I didn't draw a very nice rectangle, but you can draw a better one. I aimed it to be along this line of 0.6. So half squares, I can say this is 1, 2, 3, 4, no, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, approximately 19 small squares. So area of half of those squares which are not full will be half of the area of the full square. So this will be times 19. So this is the area which is above. So I'm subtracting. I'll just say 8 times 6 minus open brackets. I'll open the first bracket, 0.5 times 3 times 5.4. Plus I open another bracket, 9 times 0.04. Plus I open another bracket, which is 0.5 times 0.4, I mean 0.4 times 19. Then I close the whole bracket to find the area, which will be 39.16. So this is 39.16, or approximately 39. So the area there is 39. Okay, so you can use any other method. Somebody would prefer to draw another person would choose to draw a triangle or a rectangle inside. Somebody would choose that, okay, me, I will draw a rectangle inside. So they will draw a rectangle inside here and maybe draw off a triangle here. So they first find the area of this rectangle, the area of that triangle, and then now they count the small squares remaining there. But remember, you need to know the area representing one small square. Then you add to find the total distance, because distance is the area under the graph. Okay. Next, the bicycle and the cyclist have a combined mass of 92 kilograms. The vertical height through which the cyclist moves is 1.3. For the movement of the bicycle and the cyclist between t equals to 0 to t equals to 8 seconds, use the figure to calculate the change in kinetic energy. So we know that the change in kinetic energy is going to be equal to, since kinetic energy is a half mv squared, so the change in kinetic energy will be equal to a half times the mass, which is 92. Then there should be a change in velocity. Between t equals to 0, the velocity is 6, and that will be 6 squared, and t equals to 8, the velocity is 3 from the graph. So that would be minus 3 squared. So we just press our calculator, 0.5 times 92 times 6 squared minus 3 squared. That is 1242. So that is 1242, which is 1240 to 3 significant figures. Calculate the change in gravitational potential energy. So we know that potential energy is equal to mgh. So this is going to be m, which is 92, g, which is 9.81, times the height, which is given as 1.3. From the question, it is 1.3. So 92 times 9.81 times 1.3, which is 1173. 1173, or approximately 1170 in joules. The cyclist pedals continuously so that the useful power delivered to the bicycle is 75 watts. Calculate the useful work done by the cyclist climbing up the slope. So they have told us the cyclist pedals continuously so that the useful work done by the cyclist climbing up the slope is 75 watts, and we want the work done. I think this question was repeated, so I'll use the second part. So we know, me and you, that power is equal to the rate of transfer of energy, that is energy transferred by time, which is the work done over time taken. So we want the useful work done, which is going to be the power times the time, and the power is equal to 75. The time was given is from 0 to 8 seconds. Time is from 0 to 8 seconds. So that would be times 8. So that would be times 8. So 75 times 8, that is 600. Some energy is used in overcoming friction. Use your answers in B to show that the total energy converted in overcoming friction is approximately 760 joules. So we have seen, in part B, we have seen the change in gravitational potential energy is 1170. We have also seen that the change in kinetic energy is 1260. But we have seen the work done, the useful work done by the cyclist in climbing up the slope as being 600. So the useful work done, if the useful work done is 600 and the change in kinetic energy is 1240 kilograms, so the question is telling us to use the answers in B to show that the total energy converted in overcoming frictional force is going to be equal to 670 joules. So the change in kinetic energy, because the speed decreases, plus the work done in climbing, minus the gain in potential energy should be equal to the total energy converted in overcoming frictional forces. Because if the work done, if the change in kinetic energy plus the work done in climbing is not equal to the gain in potential energy, then it means part of it must have been used in overcoming friction. So the change in kinetic energy plus work done in climbing minus the gravitational potential energy should be equal to the total energy converted in overcoming friction, should be equal to the energy in overcoming friction. Should be equal to the energy in overcoming friction. So it means that energy in overcoming friction should be equal to the change in kinetic energy was 1240 plus the work done by the cyclist climbing up the slope, which was 600, then minus the energy which was converted into, which was equal to the change in gravitational potential energy, which is 1170, and we can check. So 1240 plus 600 minus 1170, that is equal to 670. So the change in kinetic energy plus the work done in climbing should be equal to the gain in potential energy if there is no work done against friction. But since there is work done against friction, then it means the change in kinetic energy plus work done in climbing minus the gain in potential energy is equal to the energy in overcoming the friction force. Determine the average magnitude of the frictional force. Since we have the work done against friction force, so the frictional force is simply going to be equal to the work done divided by the time taken. So the work done is 670 and the time taken is, what was the time taken? Not, it's not time taken, it is distance. Work done over distance, not time taken, because work done is force times distance, then the frictional force will be work done over distance, and we have calculated the distance above as 39. And we can check, divide by 39, which gives us 17 newtons. So that is 17 newtons. Suggest why the magnitude of the total resistive force would not be constant. Of course, it cannot be constant, because if the speed increases, since there is change, or if the speed decreases, because the speed changes from 6 to 8, this to 3, the speed is decreasing. A decrease in speed means the air resistance decreases. If the air resistance decreases, then it means the magnitude of the resistive force cannot remain constant, because the frictional force is decreasing. So we can simply say that since the frictional force includes resistance, or frictional forces include air resistance, frictional forces include air resistance, frictional force includes air resistance, and air resistance decreases with decrease in speed, and air resistance decreases with the decrease of speed. So it means the frictional forces, the frictional total resistive force cannot be constant. So total resistive force cannot be constant. Frictional forces are including air resistance, but earlier on we have been seeing air resistance is directly proportional to the speed. Since the speed decreases, it means the air resistance decreases. Therefore, the total resistive force cannot remain constant. Okay, distinguish between scalar quantities and vector quantities. So we know scalar has only magnitude. Vector, this one has both magnitude and direction. In the following list, underline all the scalars. Acceleration is a vector, force is a vector, kinetic energy is a scalar, mass is a scalar, power is a scalar. So the weight is a vector because weight is a force. A stone is thrown with a horizontal velocity of 20 meters per second from the top of the cliff, 15 meters high. The path of the stone is shown here. So you can see the path of the stone. Air resistance is negligible, so it means acceleration is constant, 9.81. For this stone, calculate the time to fall 15 meters. So since 15 meters is in the vertical, we shall consider vertical motion and use S in the vertical is equal to initial velocity in the vertical times t plus a half acceleration in the vertical times t squared. Vertical displacement is 15. Initial velocity in the vertical is 0 because the stone was thrown horizontally. So this part will be 0, remain with a half times 9.81 times t squared. So it means t is going to be 2 times 15 divided by 9.81 under the square root. So square root of 2 times 15, 9.81. That is 1.7487 or 1.75 or 1.7. So I'll take 1.75. Calculate the magnitude of the resultant velocity after falling 15 meters. Resultant velocity. The velocity in the horizontal does not change. It remains constant 20 meters per second because there is no acceleration in the horizontal because there is no resultant force in the horizontal. But the velocity in the vertical changes because there is an acceleration in the vertical. So velocity in the vertical will be initial velocity in the vertical plus twice. I'm using v squared. Since I have the time, I could even use v equals to ut. But let me use v squared equals to u squared plus 2as. I'm using the vertical. So v in the vertical is going to be the square root of initial velocity in the vertical is 0. So I remain with the 2 times 9.81 times s in the vertical, which is 15. And this is square root of 2 times 9.81 times 15, which is 17.16. So I'm now finding the resultant velocity. V resultant is going to be the square root because these are vectors. So this will be the square root of v in the x squared plus v in the y squared. That will be the square root of 20 squared plus 17.1 squared. So that is square root of 20 squared plus 17.16 squared. That is 26.3 or approximately just 26. Describe the difference between the displacement of the stone and the distance that it travels. So in other words, we are distinguishing between displacement and distance. Of course, if I was to go to the diagram, for the distance, I would find the length of this curved path. For the displacement, I would draw a straight line from the initial point to the point where the object lands. So you see, this will be the displacement, the other one is going to be the distance. So this distance is the length of the actual path traveled, while displacement is the straight line distance between the start and the finishing point. So distance is the length of the actual path traveled. Then displacement is the straight line Displacement is the straight line distance between the start or the starting point, the starting and finishing point. In fact, we can simply say displacement is the shortest distance between the start and the finish points. Shortest distance between start and the finish points. So that is the meaning of displacement. The shortest distance, which is going to be actually the straight line distance between the start and the finish points. Okay. A sphere of radius r is moving through a fluid with a constant speed v. There is a frictional force F acting on the sphere, which is given by that expression, where d depends on the fluid. Show that the SI base units of d are those ones. So one, we can first of all list the units. For F, it is force, which is kilogram meters per second squared. For R is radius, which is meters. Then for V, it is speed, which is meters per second. So what remains to make D the subject? Making D the subject, D is equal to F divided by 6 pi times R times V. So the units of D will be F is kilogram meters per second squared divided by, we ignore 6 pi in the units. So R is in meters times V, which is meters per second. So we simplify this, one M has cancelled. So it means the units of D will be equal to kilogram. There's M at the bottom, so it becomes M power negative 1. S power negative 2 divided by S power negative 1 becomes S power negative 1. So those will be the units. A rainy drop of radius 1.5 meters falls vertically in air at a speed of 3.7. The value of D for air is 6.6 times 10 power negative 4 kilograms per meter per second. The density of water is 1000 kilograms per meters cubed. Calculate the magnitude of the frictional force F. Calculate the magnitude of the friction force F. So we have seen that F is given by 6 pi times D times R times V, which is going to be 6 pi times D, which is 6.6 times 10 power negative 4, then times R, which is 1.5 millimeters, that is 1.5 times 10 power negative 3, then times V, which is 3.7. So we have 6 pi times 6.6 exponent negative 4, then times 1.5 exponent negative 3, then times 3.7. So that is 6.9 times 10 power negative 5. Calculate the acceleration of the rainy drop. Acceleration of the rainy drop. Let's first look at the rainy drop. So the rain drop is falling downwards. Its weight, which is mg, is vertical downwards. And then the frictional force is going to be in the opposite direction, upwards. And remember the resultant force, so this is friction force F. The resultant force is equal to mass times acceleration, which is the difference between these two. So the resultant force, I'll use Fr for resultant force, which is given by mass times acceleration, is going to be equal to the weight downwards if the drop is moving downwards. So it is mg downwards minus the frictional force F upwards. So which means we can now find the acceleration from, you can divide this by m by m by m. So the acceleration is equal to g minus f over m. Remember, m is equal to the we can find m from m is density times volume. Because it is a rainy drop, we can assume it is spherical. Where should I find? Okay, the mass m is equal to density times volume, which is equal to the density times 4 over 3 pi r cubed. So that is, since they gave us the radius, the density of water is 1000, so we can now find acceleration as being equal to g, which is 9.81 minus, open brackets. In the numerator I have f. F is 6.9 times 10 power negative 5. In the denominator I have the mass, which is density times volume. So the 3 goes up, so I will say times 3 upwards, so that in the denominator I remain with the density, which is 1000 times 4, sorry, this is 1000 so density is 1000 times 4 pi times the radius, which is 1.5 times 10 power negative 3, and this is raised power 3. So that is our expression. So we can now find the acceleration here. Let's begin with the bracket. So we have 6.9 exponent negative 5 times 3 divide by, so we have, I will open two brackets. Okay, I can just say divide by 1000 times 4 pi times, open a small bracket, which is 1.5 exponent negative 3, but this is raised to power 3. Then I close that bracket. So the denominator has, when we divide, we get that. So we must have 9.8 minus that answer. 9.81 minus the answer, to gives us 4.93. So the acceleration here is 4.93. 4.93. That is the acceleration there. Okay. And the variation with time t of the speed v of the rainy drop in A is shown in the figure here. State the variation with the time of the acceleration of the raindrop. So you see the gradient is decreasing. And remember, of course, at t equals to 0, acceleration is going to be g. But then, as time goes on, the gradient is decreasing, meaning the acceleration is decreasing. It is not going to be less than g. After some time, somewhere here, we see that the line becomes horizontal. That means now the acceleration is equal to 0 because it was decreasing. At that point, the air resistance is equal to the weight. Therefore, the acceleration will be 0. Okay. So we start by saying at t equals to 0, acceleration is equal to 9.81 meters per second squared, that is g. Then the acceleration decreases with the time as air resistance increases with the speed. then let me remove this. And then acceleration decreases with the time as air resistance, or since air resistance increases with the speed. As air resistance increases with the speed. Remember, the weight is constant, but air resistance increases with the speed. When the speed increases, air resistance is increasing. So it means the acceleration decreases because the resultant force decreases. So as air resistance increases with the speed, until a point when the weight, the force due to air resistance equals to the weight. Force due to air resistance equals to the weight and acceleration goes to 0. So when the air resistance equals to the weight, then the acceleration goes to 0. But as the speed increases, the force due to air resistance also increases because air resistance increases with the speed. The point is going to reach when the air resistance is equal to the weight, and then the acceleration goes to 0 because when the air resistance equals to the weight downwards is balanced with the force due to air resistance. That means the resultant force F is equal to 0, and F is mass times acceleration. The acceleration will be 0. The speed is constant. That's why you see the graph becomes a horizontal line. The graph now becomes a horizontal line, which means acceleration here is equal to 0. Let's stop part 1 at this point. A second raindrop has a radius that is smaller than that given in A. On the figure, sketch the variation of speed with time t for the second raindrop. It has a radius that is smaller. If the radius is smaller than that given in A, it means the air resistance is going to be less. The air resistance is going to be less because the volume is going to be smaller. But it will also reach terminal velocity. So because the air resistance is going to be less, the graph for the second one is going to be on top of the first one. The second raindrop has a radius that is smaller than that given in A. The radius is smaller, so the surface area has reduced. So the air resistance is going to be less, but the density has remained the same. If the density has remained the same, because it is still the density is still the density of water, so mass is equal to density times volume. The density has remained the same, but the volume has decreased. It means the mass may have decreased because the volume has reduced, but the density is the same. The mass may have reduced, so the weight is smaller, and the air resistance. Oh, by the way, here since the weight has reduced, the surface area is smaller. The air resistance is supposed to be smaller, but the weight has also reduced. So it means the second graph is going to be below the first one. So we shall have a graph which is below this one. And it will also reach terminal velocity. So it may reach a smaller terminal velocity than the other one. If air resistance is not negligible, then a lighter object will reach a smaller terminal velocity. Okay, let part one stop there, and we shall speak from there in part two. Have a blessed day. Bye bye.